We have seen that to minimize the mean square error, we obtained an estimator, which is in general the optimal estimator is a nonlinear function. So we saw that the optimal estimator, when you see the optimal, was if you want to estimate y, so you have to calculate integral of y fxy of x and y dy divided by fx of x, and y varies from minus infinity to plus infinity, and this was the expected value of y given x equal x. So this is in general nonlinear function, and if we don't know the joint distribution of the two random variables, which is not always practical. In cases which this function is available or you have ways to calculate it, this is really a good estimator. For instance, using machine learning and so on, if you have lots of data, you could try to form this function and obtain the optimal estimator. But if not, then this is not practical. The practical way is to use a linear estimator. So the linear estimator, linear mean square error estimation, is that you could assume that my estimator is a function of x, a linear function of so here this is ax plus b is my estimator, and again I want to minimize y minus c, and c is a x plus b, and I want to minimize mean of the squared error. So if I minimize this one, then here in order to determine this estimator, provided that x is known, I only need to determine the values of a and b. So this is how we formulate that. And remember that this c is a function of a and b. So when I do this minimization, my objective is to calculate the coefficients of this linear combination. So the problem is to find the constant value which minimizes the mean square error. So we have to, so this is the true value, this is the estimator, and we want to find a and b which minimizes this function. So if you want to minimize this function, you have to calculate derivative of this function with respect to a, whatever it is, set it equal to 0, derivative of this function with respect to b, and set it equal to 0. The first one gives you one equation, and the second one gives you second equation, and you have two unknowns, two equations. You solve it, and then you find the optimal values. So if you do calculate the derivative of this with respect to a, you find this equation and you set it equal to 0. And if you calculate the derivative with respect to b, set it equal to 0, you find this one. So you have two unknowns, two equations. So you see that these minus 2 are constant. You can get rid of them. So from here we can get these two equations. And remember that if you have some information about the joint distribution, we could obviously calculate mean of y, mean of x. Here you can calculate the cross correlation between x and y, and then this guy is equal to that, so the power of x and the mean of x. So this is a set of equations. In order to solve it, we see that these set of equations are linear with respect to a and b, so we can write them in a matrix form. So we see that if I write a and b as a vector, this guy is equal to mean of x times b and b 1, and then the second one is mean of x to the power of 2, and then you have mean of x. So if I multiply this matrix by this vector, this side, the first one multiplied that gives you this expression, and the second one gives you this expression. So this should be mean of y, and this one should be mean of xy. So obviously in this equation, so you have this vector is unknown, and this is a matrix. So obviously, if you multiply both sides by the inverse of this matrix, you get AB is equal to inverse of this matrix, which is mean of x 1, mean of x to the power of 2, and mean of x, inverse of this matrix, and then mean of x, y, mean of x, y. So if you do inverse, and if you multiply the inverse by these, you get the solutions easily by that. So the optimal value of A will become equal to this one, and the optimal value of B is equal to that. So obviously the optimal estimator will become A optimal value, which is given here, times x plus B optimal value, which is given here. So this is your optimal linear estimator. We call it linear estimator because here you have a linear combination of the observed information. So, so if I put this pair of optimal value back into my criterion, so if I put these two values, these optimal values from here, if I put it here and here, I will, and then calculate the mean of this guy, I will find the minimum attainable, the smallest value of MSE which could be obtained using a linear estimator can be calculated. So, so the minimum attainable or minimum mean square error estimator, we call it in brief MMSE, is calculated, and this will become equal to that, which is equal to the variance of y times 1 minus rho xy. So you see that this is the variance of y and the whole thing is the variance after the linear estimation. So so this is the conditional variance of y when you do the optimal estimator. And you see that the variance is decreasing because this guy rho is absolutely smaller than 1. So what is happening is that a random variable x can be viewed as a vector. Number 1, it can be viewed as also another vector. So, and then this is random variable y. So that means that you multiply random variable x by another value a, and multiply in this direction, you get the length of b, and then this guy, the linear combination will become, this is ax plus b. So this is going to be your estimator. And this estimator is optimal when the error, and this is the estimation error, which is equal to y minus c, when this length of this is minimized. So this length is minimized is if this vector, if the error is perpendicular to these 2D planes. So if you consider the plane which contains vector x and vector 1, if this plane is perpendicular to error, if the error is perpendicular to x, if the error is perpendicular to 1, then this C is optimal. So the optimal estimator or optimal linear combination is obtained when your error is, and this concept that error is perpendicular to the observed value, because x is an observed value, 1 is a constant which is observed value, then the error is perpendicular, is orthogonal to your input data. So this is sometimes referred to observed value or input data. Input data or known data. We call it principle of orthogonality. So what we have is that we have 1 and x as input, and then you multiply these by a, and multiply these by b, and then add them together, and then you obtain your estimator. And then you calculate the error between the true value y, you get your error. When this error is orthogonal to these inputs, and this is the output error, we know that this optimal estimator is this estimator is optimal. So something in practice is that quite often they look at these error and then they change these coefficients, tune these coefficients in order to make this error orthogonal to the input, or minimize the energy of this error. So it's like that you have certain equipment like your TV, and then you have a couple of constant here, so you adjust them with a screwdriver or with your computer, and then try to see if the energy here is reducing or increasing. As long as this is reducing, you are tuning these parameters to be optimal. So this is the main principle of machine learning, adaptive filtering, and many other signal processing tools that you have available to you. So, this concept of orthogonality is called principle of orthogonality. So this result can be easily generalized to more than 2 dimension, to like n dimension, m dimension, and is quite useful. So this is a diagram. So this is like your random variable x. If you multiply it by constant, so it's going to ax is going to stay on the same direction, and if this is b, if you multiply it by b, you stay in this direction, and your estimator y hat or c is ax plus b. So 1 and x are 2 vectors, and if this is perpendicular, if this red line, which is your error, is perpendicular to your green line and is perpendicular to your brown line, so the error is perpendicular to the hyperspace of input data. So error is perpendicular to the hyperspace of input data. And this is what most learning algorithms they try to achieve. So from vector representation and geometric interpretation, we conclude a similar principle. The MSE is minimized, and you see that this if this is perpendicular, you could say that this length or mean of y to the power 2 is equal to this length to the power 2 plus this length to the power 2. So basically, you could say that this is equal to mean of y hat to the power of 2 plus mean of the error to the power of 2. This is only true when your estimator is optimized. So obviously, from here you can calculate the energy of the error is the difference between these two guys. So from here you could say that the minimum attainable error is the difference between, so basically this is an abbreviation for mean of y to the power of 2. Okay, so this is like a norm, and this is mean of y hat to the power of 2. Okay, so this means that y hat is the projection of y over the hyperspace of the input data, and error is the orthogonal projection of y over the input data. So you for this one, you see that this point is the closest point to this one. So if you want to find the closest point to this 2D space, okay, y hat, this will become orthogonal. that means that you have to do an orthogonal projection. And because this is an orthogonal projection here, so this notation here means that you subtract y minus y hat. In summary, this error is orthogonal to this vector 1, and the error is orthogonal to vector x as well. In this example, error may be orthogonal to 1 or not. So remember that the PDF of 1, if you treat 1, a constant number, as a random variable, is a degenerate random variable because all the mass of probability is concentrated here at 1.